In synthetic optical holography. Please join me in welcoming Brad Duetsch.
For the first part of my talk, I'll be miking myself. All right, let's see here. This is on. This one's always on, they told me. And I have to get rid of my jacket because I just found out this is being recorded, so I'm a little bit sweatier than I was. Okay. Yes, thank you for the nice introduction. I've been at Beckamn for 2 years now, and I work with Rohit Bhargava and Scott Carney. And with Scott, I work on optical inverse problems, and this is one of them called synthetic optical holography, or SOH for short. In SOH, we assemble a hologram, an optical hologram, point by point, rather than doing it as a wide field technique. And there are a number of advantages to that. Lets us do holography in cases where it would be very difficult to make a reference wave. So before I talk about that, I want to do a little intro on digital holography. Show of hands, just so I have some idea, who's a little bit familiar with digital holography? That guy? Okay, that's one. Okay, very good. Okay. So the whole premise is this. Suppose we have some object here that's an electrical field or electromagnetic field, and it has an amplitude and a phase that depends on position. There are lots of reasons we would want to record the amplitude and phase. Maxwell's equations tells us that if we know the field here, then we know it everywhere in space. So if we can figure out that field, we can refocus it, we can do tomography, that is make 3D images of something. We can correct aberrations. But there's a problem, which is when we image this on a CCD, for example, the CCD doesn't record the field, the complex field, it records intensity, time-averaged intensity to be specific. And so we'd like some way to encode both amplitude and phase instead of just intensity. And holography is one way to do that. So what we do is we image this object on a CCD, and then we come in from the side. There are a lot of variations of this, but this is one basic one, with a plane wave reference. And the two fields interfere. And they make this sort of stripy pattern. If you can look at that without having a seizure, you'll see the error encoded there. And this, I've made this into a phase object. So it has 100% amplitude transmission, but it changes by phase. And you can sort of see an outline of the arrow. And the phase is encoded as a little shift of that reference. So let's look a little bit more in detail at how this gets recorded, or how the phase gets encoded. The intensity this should be a proportional to sign. I always forget that. We optics people always forget that. Is just the sum of these two fields, absolute magnitude squared, and actually time averaged. I left that out. And you end up with 4 terms on the right-hand side. 2 of them represent the intensities of the signal in the reference. And then the last 2 are called interferometric terms. They're proportional to the fields rather than to the intensities. And we need some way to extract those. So here's an example where we have a phase object. Like I said before, 100% amplitude transmission. Doesn't have to be, but it is in this case. And we come up with this reference phase. So if you look at the zoom in, it's a reference ramp. And every 2 pi radians, it resets. They sit on top of each other. They get multiplied together and added together and squared. And you can see the same equation on the bottom. We have our 2 non-interferometric terms and 2 interferometric terms. That's what the intensity looks like over on the right. It looks like slow oscillations, but they're actually very fast oscillations, so I zoomed in there. And then to retrieve the amplitude and phase, we take a 2-dimensional spatial Fourier transform. Fourier transforms are a way to plot the spatial frequency content. Slow variations up here, like the sand over here, the sky, end up in the middle. And fast variations, like sharp edges, end up toward the edges. And what we find is that those 2 intensity terms, the first 2 terms, end up stuck right here at DC, right in the middle, with no variation, or very little variation. This guy is the autocorrelation of the sample, so it actually does vary, but it's very weak because the reference is considered much bigger. And then these 2 interferometric terms is this blob and this blob. So if we look at either one of them, we find something that's proportional to what we want, to the complex field. So to get it back, to get the complex field back, all we have to do is throw away everything else, shift one of these back to the center, and then inverse Fourier transform to get the field back. So here's an example of what that looks like. On the top row, we see the reference, see the intensity that's recorded, the Fourier transform of the intensity, and then the retrieved phase. So on the top, I've taken a really fast reference oscillation. And what happens over in the Fourier transform is that those two blobs are really far separated. The faster you oscillate, the further they are separated. The red box is our filter that's going to throw away everything outside the red box and only keep what's inside. Shift it to the center, inverse Fourier transform, and you get the retrieved phase on the right. The point of this slide is that the size of that box and the separation of these two blobs are very important for the retrieved image. If we slow down the oscillation, so instead of oscillating quickly, ramping quickly, we ramp slowly, what happens is these two blobs get close together. Well, if we try to throw away everything outside the red box, what will happen is we still get both of those blobs. We still get both of those contributions. And the one we don't want, the left one, shows up in the retrieved phase. In this case, it looks like just oscillations. But even if you were to filter out that frequency of oscillation, you would still see interference between those two things. So another option would be to make the box smaller, make the filter smaller, and only catch one term. Well, if they're not very far separated, that box has to be really small. And the size of that box is our pass band for spatial frequencies. Everything outside of it is sharp edges, everything inside is smooth things, and so what we get out is all smooth. We've thrown away our high spatial frequency information, which is our sharp edges. So if we want to separate this really far, what we do is tilt the reference wave a little further. If we were to have a reference wave that came in straight on, there would be no oscillations, and as we tilt it, they get faster and faster and faster. Well, what's the fastest they can oscillate? That would be if the reference wave were to come in exactly perpendicular to the CCD, right? And the oscillations in that case would be one wavelength. You can't get any faster than that in free space. And that's what this circle represents. That red circle represents an oscillation of one wavelength. Well, that is what causes the diffraction limit, if you've heard that for imaging or microscopy. Anything outside that circle, you can't record information about spatial frequencies faster than that. So information about sharp edges are lost in microscopy and in imaging. And similarly in holography, we can't separate those two contributions further than the radius of that circle, or the diameter of that circle, I should say. But suppose instead of doing this on a CCD, we were to do it one point at a time and just choose whatever we wanted the reference to be at that point. Well, it would look something like this. On the right, we have an object, and it gets scanned point by point. And we focus light down and address one point on that sample. The scattered light is collected, and it's combined interferometrically with a reference. So light comes in here, gets reflected off a beam splitter, then a mirror, and then gets interfered on a point detector. That sort of pink grid is just sort of an imaginary map of the image we're going to generate. And then every time we move the sample and address a new point, we move the reference mirror a little bit and choose a new phase for that point. So if we wanted to, we could actually build an artificial plane wave. We could say at each point, we just move the reference mirror one more equal step. Move again, move another step, move again, move another step. And what we would find is that instead of being parameterized by time, we could parameterize the reference mirror position or by the sample position. And we end up with something that looks like a plane wave down here. And the oscillation frequency of that plane wave would be controlled by how fast we move the mirror and how fast we move the sample. If we move the mirror very slowly and the sample very fast, we end up with slow oscillations. If we move the sample very slowly and the mirror very fast, we end up with fast oscillations. And we're not limited by diffraction anymore. The field at the detector is still controlled by Maxwell's equations. You know, we can't get around diffraction in that sense. But we're going to cheat a little bit. And the way we're cheating is by sampling that field at different times. And that lets us choose whatever reference wave we want, whatever sample reference wave we want. And that's the basis for synthetic optical holography. This idea has some parallels in the radio. There are some references down here if you're interested, where they collect a signal and then combine it electronically. So they interfere the photocurrents or the photovoltage with another a local oscillator, and then just shift the phase at every point and create this these holography-like images. But in optics, we don't have the luxury of adding oscillating voltages together because the field oscillates so fast The detector just averages out all those oscillations. So we actually have to add the field together. So this came from the radio. It's related to digital holography, but that's actually not how we got into the business of synthetic holography. We got into it because we know some people who do near-field optics. These guys down on the left-hand side in Spain. And near-field microscopy is a way to record optical maps of an object with resolution far below the diffraction limit. So the diffraction limit will give you resolution on the order of a half a wavelength. So if you're using visible light, say a wavelength is 500 nanometers, the smallest you can resolve 2 points is about 250 nanometers. Well, lots of interesting stuff is much smaller than that. Viruses, computer transistors, carbon nanotubes. And if you want to know the optical properties of these things on high resolutions, you have to take a different approach than just standard microscopy. What they do is they take a sharp metal probe, here illustrated in red, and they raster scan it across a sample. Will you tell me when I have about 5 minutes left, by the way? Thanks. They shine light on the probe sample region, and light gets scattered away. The signal then, we know it's coming from the tip sample region. The interaction region is very small. And so our ultimate resolution is limited by the size of the tip, the radius of curvature of the tip, typically 10 or 20 nanometers, 5 to 20 nanometers, instead of the wavelength. It's in fact completely independent of the wavelength. So like in holography, there are a lot of reasons why we might want to know the complex field near the sample. It tells us the material characteristics. Is it a semiconductor? Is it a conductor? Is it an insulator? It can tell us about modes, optical modes like plasmons. And then there's another kind of technical reason, but a really important one, which is, as you can sort of see with my 2 arrows coming off of this thing, there's a signal and then a really big background. The background does not come from the interaction region. It comes from scattering from the tip or scattering from the sample. And it is not independent of the wavelength, and it is limited by diffraction. And so we want to throw away that background, but it's hundreds or thousands of times bigger than the signal. So the approach that's usually taken is the tip is modulated up and down with some frequency, here, big omega. Then over at the detector, we see that the optical signal is also modulated. Long story short, it turns out that the signal is preferentially concentrated in high harmonics of that vibration, and the background is preferentially concentrated in low harmonics of that vibration. So just by demodulating high harmonics, we get a much better signal to background ratio. Now, I said that the field is modulated at the detector, and that those harmonics I talked about are harmonics of the field. And unfortunately, detectors don't detect fields, they detect intensities. And so what happens when you add the background signal and then square them is all those harmonics get hopelessly mixed together, and you can't distinguish between them by harmonic. So we need to record a signal that's proportional to the field rather than proportional to the intensity. So that sounds like holography. Traditionally, though, it's not done with holography. It's done with other kinds of interferometry. This is an example of a phase shifting technique where we use a microscopic interferometer and interfere the signal and the reference just as before. And then at every pixel, we dwell on one point of the sample and we move the reference mirror. Well, from our microscopic interferometer theory, we know that that's going to sweep out a sine wave. And that sine wave has an amplitude and a phase and an offset. And by taking enough points on that sine wave, at least 3, but up to hundreds, we can fit that function and figure out what those 3 parameters are for every pixel. Now, that works okay. I mean, it works fine. I did my PhD on it. I hope it works. But the problem is that now we have to take a whole bunch of data, at least 3, but again, up to hundreds, at every point on the sample, and that seriously slows down the acquisition. There are some other techniques, pseudoheterodyne and heterodyne interferometry, that will also do this, but again, you have to take multiple data at every pixel. Synthetic holography, on the other hand, only takes 1 datum per pixel. And the secret here, the reason we're able to get away with that, is we're spreading out the phase information among neighboring pixels, among multiple pixels. Instead of taking them all at 1 pixel, we're spreading them out and using the mutual information against, of them to get the information. We're buying that at the cost of bandwidth, of spatial bandwidth. Remember, we had that red box as the filter. Well, the biggest that can ever be is half of the Fourier space. So we're always throwing away half of the Fourier space. So we're trading time for bandwidth, essentially. So in nanoholography, all we do is replace that object with our tip sample region. And we raster scan our sample just as before and generate an image. So to test this out, we started by looking at resonant optical antennas. This always takes such a long time. These are so huge. I really should just copy paste it as a new image, but I never get around to it. On the top, you see a gold optical antenna on an insulating surface. And we're illuminating it with light and then taking our holographic image. So you see these bands that going across. That's the intensity pattern. If we take a two-dimensional spatial Fourier transform of that, we get the blue with rainbow images. On the right side, there's a zoom in. In the center is that DC term that has the intensities, and then our two blobs up and down from that. And all we need to do is filter out one of those, shift it to the center, inverse Fourier transform, and we get a field of complex numbers. And that's what's shown on the bottom, the amplitude and the phase from those complex numbers. The sort of hot spots you see on the amplitude, the is hot spots, and we expect them wherever we have a lot of free carriers. And on the bottom, you see this blue-red pattern, and that represents an oscillating dipole. So this is just a dipole antenna, and the reason we start with this is because we know how dipole antennas work, and we know what we expect to see, and we've done this with all kinds of other techniques, and this just verifies that we don't see anything crazy using holography. Moving on, these are some zinc oxide nanowires. They're growing out of the board, and they've been cleaved and then polished. So we're looking at all the end facets. And in the bottom right, this is a zoom in, the amplitude image on the left-hand side there, A sub S, again maps the free carrier density, and we see them around the edges. Now that's kind of cool, but it's not actually the cool thing about this image. The cool thing is that you get about 3 or 4 hours to take a near-field image. That's about how long it takes for things to start drifting. Your interferometer alignment drifts, your sample drifts, things heat up or cool down, the air conditioner kicks on. And so typically near-field images are limited to tens of kilopixels, let's say 40 to 100 kilopixels. This image, however, is 10 megapixels, which we took in the same amount of time. And that's just because instead of sitting at 1 pixel and taking a whole bunch of data, we take one data point, one datum per pixel and move along. And so we're taking advantage of this multiplexing, this spatial multiplexing, to generate these huge images. So you can either, if you have that much time, you can either take a really big image, or you can take a really small image a whole bunch of times. So it provides the opportunity to start looking at dynamics. So this is what happens if we look at those zinc oxide nanowires and start heating them very slowly over the course of 5 or 10 minutes. They go through some kind of phase transition, and I'm absolutely not qualified to talk about it. But the point is that synthetic optical holography opens the door to this kind of analysis, whereas it would be very difficult before because it would take around 40 times longer to scan this. How am I doing on time? 7 minutes, okay. There's also no reason we can't just plop another laser in this setup simultaneously and record multiple wavelengths. I showed you the Fourier space with the blobs. This is a simulation where in the center, top left, in the center is the DC term, and then you see these other two blobs on the right. As we start moving the reference mirror faster, you'll see them start to separate, and each one of those points is a different wavelength. This is a 2-wavelength experiment. By changing the scan speed and by changing the mirror speed, we can control where those dots land in Fourier space. So if we want to, we can separate them maximally, and then each one gets as much bandwidth as possible, and we can start adding more and more frequencies into this. The analysis is exactly the same as the single wavelength case. You just use more filters. You shift them back, you inverse Fourier transform. Here's a concrete example of that, where on the right side, top and bottom row are 2 different wavelengths. And it's maybe a little tough to tell, but the response of this material is different at these 2 wavelengths. This is graphene again. And this gives us an opportunity to do spectroscopy. In a single scan, you can get a spectroscopic image of your sample. An interesting thing to note here are these dark lines across this image. So we're raster scanning like this, back and forth, and then going up and up and up. These dark lines represent cases where the reference mirror has been moving forward, reaches the end of its travel range. It's mounted on a piezo, has to retract, start again. Has to retract, start again. So it would be great if we didn't have to use these long travel range closed loop piezos. And if we didn't end up with these dark spots in our image, of course they can be filtered out or whatever. We can be very careful about retracting, resetting the scan, doing it again, and making sure they match up. But an alternative is, well, as long as we have complete control over the reference wave, why don't we just pick a different reference mirror motion? Instead of moving it linearly, oscillate it sinusoidally. It would be over a short distance, so we don't need to operate in closed loop, where the piezo, so we don't need to worry about the piezo going nonlinear, for example, or drifting, or hysteresis. And we don't have to worry about having a long travel range. So the difference between a short travel range open loop piezo and a long travel range closed loop piezo is about 10 grand. So this becomes a much cheaper experiment to do too. Unfortunately, we have to modify the inversion a little bit. We can't just take a Fourier transform, filter, inverse Fourier transform to get it back, because when you modulate the reference sinusoidally, you get all those extra terms that are illustrated right here in Fourier space. And the distance between the terms is controlled now by how fast the mirror is moving. Five minutes? Okay, good. Is controlled by how fast the mirror is moving, as opposed to the linear case on the left, where it was controlled by the wavelength and the scan speed. Now, instead of taking a single image, the math works out that a single term in Fourier space, the math works out that we have to take at least two. We can think of them as odd and even terms. We have to take one odd one and one even one. And those represent the real and imaginary parts of the complex field. This is similar to pseudo-heterodyne interferometry, if you've seen that, except that's typically done in the time domain. So you would record a temporal signal and then do a filter on those two terms. This is now a spatial filter. It's important to point out that, and it may be hard to see in this resolution, but the images, the retrieved images on the right are a little bit blurrier than the images on the left. So what's going on there is the red boxes have to be smaller, our filters have to be smaller, which means that we're low passing the object. So we're essentially trading convenience for bandwidth. However, we could get around that by just oversampling the image by a factor of 8 or whatever. The cost of doing that is that the scan would take longer. So there are a whole bunch of trade-offs here, but this is one more opportunity for doing synthetic optical holography, and in this case with a nonlinear reference phase. We're looking at some other ideas here. So for example, why not just put the reference mirror at a random location at every pixel? Then you'd be sort of projecting your image on some kind of a mask, like a Hadamard mask, for example. And there may be some interesting applications there too. So far I've talked about near field, and I just want to have one slide here showing that this is actually applicable to any scanning optical interferometric system. So for example, confocal microscopy. Here is just as a cute example. We're looking at, actually, some of you, oh yeah, never mind. It says cantilevers at the bottom. I was going to quiz you. Oh well. If you do AFM, atomic force microscopy, or in fact near field, you'll be familiar with these guys. We're looking, I think from the top, yeah, we're looking from the top at a cantilever. So there's a silicon chip over here, and then an aluminum cantilever, very thin aluminum cantilever out here. And this gets shaken very, very gently, but very fast at its resonant mode, or in fact, in this case, 10 times the resonant frequency. And then by doing a holographic reconstruction, we can raster scan this, move the reference mirror linearly, and then we can demodulate at each pixel at harmonics of the resonance frequency. And what we find is that we get a stroboscopic effect. So at each different frequency we demodulate, we see a different resonance pattern of the cantilever. So the point of this is just to demonstrate that we're not limited to near field. We can do confocal, for example, too. So as a quick summary, synthetic optical holography is a way to do point-by-point holography. And it lets us do holography in cases where you can't make a reference wave, or it would be very difficult to make a reference wave. So for example, if you're trying to exceed the diffraction limit, or if you want something that's not a plane wave. And in fact, it doesn't have to be something that can be that is allowed by Maxwell's equations in a plane. It's not an analytic signal. It's a sampled analytic signal. So you really break the boundaries there. It's faster than doing interferometry on the same size. So that lets us do dynamics. It lets us take big images. It's relatively simple, just a Michelson interferometer. And in fact, with the linear case, you don't even need to synchronize anything. You just say, I want to move my reference mirror linearly, and after the fact, look at the Fourier transform and figure out where your terms are and filter them. And it's adaptable, particularly to multi-wavelength analysis. Okay, thanks for your attention.